Okay, good morning. I'm David Laws, curator at the Computer History Museum in Mountain View, California. It's October the 27th, 2010, and we're here today to record an oral history of Stephen Hofstein, who was a pioneer in MOS technology at RCA and went on to have some other interesting adventures in his career that we'll cover over the next hour or so. So good morning, Stephen. Thank you very much for joining us today.
Thank you for having me, David.
Could you tell us a little bit about your childhood, when you were born, when you went to school, something about the family?
Okay. See, I was born in the Bronx, New York, in 1938, and lived in the South Bronx until I was 16. Then my parents and I moved to the West Bronx. We used to live in the East Bronx, or South Bronx, it used to be called, on 174th Street. We moved to the West Bronx on 174th Street. So it was kind of interesting. We didn't do a north-south migration. I stayed in New York. I went to Bronx High School of Science, graduated in 1959, and went down to RCA Laboratories. Went down to RCA Laboratories. I'll go back. Graduated high school and went to Cooper Union. I just almost lost my whole bachelor's degree there.
I was going to say, I think the city college comes in there
right from high school. No, RCA didn't hire us out of high school. But I went to Cooper Union in New York. Now graduated in 1959 with a Bachelor of Science in Electrical Engineering and went to work at RCA Laboratories. I had worked for RCA Corporation.
And that's the school that's called the City College in New York today?
No, Cooper Union is Cooper Union. It's called the Cooper Union for the Advancement of Science and Art.
Okay.
It was a school established in 1859 by Peter Cooper, who liked to call himself a mechanic of New York. And he created a school which was unique in many respects. The first being that it is a full scholarship school. All students there are on full scholarship. Okay. There are no tuition. The only thing you have to pay is your expenses, your books and such like.
Believe it or not, Stanford used to be that way.
That I didn't realize.
Very different today.
Yeah, it really is.
And so this was 59, you graduated from Cooper Union.
Right, with a BSEE.
And why did you go to that college and study that subject? Was there someone in your life, an uncle or a mentor or somebody that steered you that way?
I always loved electronics. And my dad worked for the U.S. Post Office. We were not wealthy people by any means. We had a 3-room apartment in the East Bronx that I grew up in. And I loved the mystery of technology, and focused rather early on from, chemistry, of course, is always interesting. You make things blow up, and that was a lot of fun. But as I got a little bit older and began to worry about losing my fingers, I kind of decided to do electronics instead. And it was a wonderful era because the war had ended, and tons of war surplus material, electronic material, made its way down an area called in Cortlandt Street in Lower Manhattan. And you would go down there and walk the streets, and they had all these stores selling boxes and boxes of receiving tubes, all the stuff left over from the war that now is war surplus. Mm-hmm. You could buy a 6AU6, I don't know why I remember that tube, I like it was a good one. They don't make them anymore, receiving tubes. This is a little, I guess they called them an acorn-sized tube, and you get it for 5 cents. Didn't know what to do with it, but I had it, and that was very exciting. I used to take it out and look at it all the time. So I began to play with circuits and get my batteries, and I really fell in love with electronics and electricity and all the miracles that were associated with that. So I was kind of hooked on electronics. Mm-hmm. By the time I came to the Cooper Union, of course, it was my desire, obviously, to become an electrical engineer.
Sure.
Although it's interesting, they gave us an orientation session, and I was sitting in this big lecture hall, and we were all filling out the form. And one question caught me by surprise. If you couldn't be an electrical engineer, what trade would you want? And I thought about it, and I thought to myself, music. That was the only thing that interested me, was music. Mm-hmm. And I often wondered the close connection that people have found over the years in terms of structure of music and science and imaging.
Sure.
Most of the great inventions came from people who saw a picture. They did not come necessarily from a mathematical equation. Mm-hmm. The equations followed the invention. For example, people knew about superconductivity before Bardeen, Cooper, and Schrieffer came up with the theory, not vice versa. And so I was at Cooper Union, enjoying it very much. Was there for 4 years, graduated in 1959, and had the option of going to one of two places that I really liked, Bell Telephone Laboratories and RCA Laboratories. And I had worked for RCA the previous summer, so I liked the people and I liked the company, but that was down in their military division in Camden, New Jersey. Mm-hmm. And of course the laboratories is considerably different. And one of the things that attracted us, and I guess all the students, were looking for some type of graduate study program. Most of the people that I graduated with, and I think a great deal of the people that came out in technology or in engineering looked towards graduate school as a necessity if they wanted to do really advanced work. And Bell Telephone had a graduate study program in collaboration with New York University, NYU, which is a very fine, very lovely school. And RCA had one with Princeton, which doesn't need any further explanation. And so it was kind of ironic because both of them made me a great job offer. And I was waiting to hear from the universities, and NYU did send me a nice acceptance letter. And I got a letter from Princeton University that said, we want to thank you so much for applying. As you know, everything is wonderful. You have a fantastic resume, but we are somewhat limited in space, so we wish you the best of luck. And I figured that's it. So I went down to Bell Telephone, and I told them I'd be joining them, and they still have the very nice acceptance letter and ready to report for duty. And I got a phone call from Paul Cumo, who was the HR person at RCA Laboratories, saying, well, when are they going to hear from me? And I said, well, Paul, when we spoke, I had mentioned to you that, the graduate study program was important. He said, well, yes, of course we know that, notified Princeton University. I said, but I got a rejection letter. He said, you got what? I said, I got a rejection letter. He says, don't go away, I'll call you back tomorrow. He didn't call tomorrow. I got a letter by messenger. They had made a mistake.
Is that right?
There was room after all. They didn't understand what happened, whatever. So now I had the problem that now
Yes.
the good news was I was going to get to go to Princeton University. The bad news was I had already accepted a job at Bell Telephone. And much to their credit, as it were, they were very gracious about it. I sent them a letter, I explained the whole thing to them, and I got a very lovely letter back saying they absolutely understood, they wished me the best of luck, and should anything ever change again, come call them. So
Great.
I had very good feelings about Bell Telephone.
Good story. And so you joined the labs, and where were the labs at this point in time?
The laboratories in Princeton, just
In
where they are
Princeton.
today.
Okay.
They're, I'm thinking, there's Princeton Borough, Princeton Junction, so it's confusing, but I do think they actually were physically within Princeton. They may not have been, because the names change as you move further out.
Yeah.
But I'll tell you, the Princeton, when I went there, which was 1959, I've been there recently, 2 different places. It is astonishing the development that has taken place over the period. I mean, when I went there, people were bemoaning about the fact that they built a bridge across the lake. Many of the scientists at the laboratories were Europeans and loved boating, and so they bought homes along Carnegie Lake, but on the side away from RCA Laboratories, whereas the Americans bought the stuff on the other side. And the reason for it was the Europeans had no problem getting in a canoe in the morning and canoeing right across the lake and park the canoe and walk to the laboratories.
Okay.
For real. So then they built a bridge, which everyone said was modernization, is totally untenable.
Sure. They're very American. What did you do initially at the labs? What was your role?
The laboratories had a, I guess called orientation, a 1-year trial period, not trial period, because they had a name for it. But when you came in, you had a choice of going to 3 4-month tours through different sections of the laboratories. It actually truly is RCA Laboratories, plural, because I think there were 7 of them at the time. 7 individual laboratories, each with its own laboratory director, and I believe he reported directly to the vice president, which was Jim Hillier. And the first one I went into was a circuits laboratory, did some work. Everyone at that time, you have to go back, the big push at that time were memories. Computers were becoming important, and memory was everything. So you had groups, there was a group doing superconductivity, and it's funny because Dick Ahrens came into that group just as I left it.
Okay.
He followed on my heels, as it were. And we were chatting about but everyone was arguing over what would make the best way to have memory. You had all kinds of phase shift dials. Anything that could hold a memory was being investigated because the need to do something other than iron cores was becoming very dramatic.
Right.
And so the second of the 2 training, it was a training assignment, was in the Electron Devices Laboratory, headed by Bill Webster. And that's when I had my first contact with the group that were making the attempts to do they didn't call them integrated circuits at that time. They were called integrated logic nets.
Mm-hmm. That was Walmart was doing some work
Yes,
there.
Warmock's group was investigating the unipolar transistor. In this case, it was the mechanical one I described to you, where they were gouging out little channels and so on. And the theory was you would take literally a rod of these things that were in series, and you would wire them up and put them on a substrate and get them to work. And it was a good idea. And theoretically, other than getting the processing under control, it would have and did perform. So I had the 4 months there, loved the work, went down to the superconductivity group, and after that 4 months was up, I made the decision to go back to the Electron Devices Laboratory.
Okay. Was there a specific project that you wanted to work on there?
Well, I wanted to work on these transistor integrated logic nets. And so I sat down in Tom's office. The first day I went back to the laboratory.
This is Tom Stanley.
Tom Stanley. And Tom was an absolutely marvelous man. I was delighted to see his interview. He's just sharp and is wonderful. If he's watching this, Tom, I miss you. You're a great guy. And I still have the original book on wine you gave me by Schoonmaker. I live with the thing. I won't give it to anybody else. Thank you. We were talking about where I would go. And Tom said, Steve, he said, would you be interested in working, and you should think about working on a metal oxide semiconductor transistor? And I remember the first thought that came to mind was metal oxide. I pictured iron rust. Honestly, how do you make a transistor out of iron rust and oxide? I don't know how iron rust will make a transistor, but I didn't say anything because I thought, it's not obviously something.
Sure.
And I said, well, that's very interesting. I said, why that? He said, I asked him, why, myself, nobody else is working on it. He said, well, there's a story that goes with that. He said, the transistor, or the concept for it's been around for a long time. And a lot of people have tried to make it work and have not succeeded. And in every case that they've tried and failed, it was kind of a career killer. He said, and so nobody here will touch it with a 10-foot pole because it's going to be death. And he said, you, on the other hand, have no career to kill. Why not? I'll never forget that. He was absolutely right. You have no career to kill. That was very true. Thank you again, Tom.
And this was 1960? Maybe?
That would have been, yes, that would have been 1960.
1960. And so...
that would have been, I guess the fall, 1960.
Doan and Kwang had already read his paper by then?
Yeah, his paper was known. In other words,
Right.
the work on the device, everyone had worked on a Marty
Yeah.
Ital and DeWarren Kong.
Right.
And the problem with it was, if you will, that it was a great concept. You could demonstrate the effect. And Carl Zaninger, in fact, took a little bar of silicon, put a gold dot on it, and reproduced what DeWarren Kong had
He
done.
made an MOS diode or something. I think
Actually,
they called that.
it was a triode. He took a small
Okay.
bar of silicon, and he welded wires to each end, and then he put a gold dot on oxide, and was able to show some modulation of current,
Okay.
which kind of reproduced what I think Kong had done, but showed the fact that there was an effect and it could be made to work, or at least it was working. I'm hesitating whether to tell the story that Carl told me. I'll let Carl tell the story. So anyway, where was I?
I was asking. Oh yeah, I was trying to fix the time when you
Yeah, it would have been a fall. In other
presented
words,
with this challenge by Tom Stanley.
Well, that would have been August of 1960
Yeah,
because the
okay.
training program was 1 year long, and I came
Right.
back right after that, so it would have been
Okay.
the fall then.
Okay.
And so they set me up, and I began to try and create the MOS transistor. And it was very fascinating because, I built the first few of them, and indeed, like everyone else saw, it was an effect, but it wouldn't work. And it took a great deal of experimentation until it finally got to work. And it was interesting because we tried everything that everyone else was trying, cleaning it, the polishing. But whatever you did, it just seemed that the states would appear. We tried wet oxidation, dry oxidation. And I think the breakthrough was really weird. It's one of these things when you think about how things are done. I always remembered metals being annealed. You would anneal things. You would forge them, you would hammer them, you create them, then you would anneal them to get the strength and so on. And so the thought occurred, why not try after the oxidation period to see about annealing it? And what was a common thing was to anneal it either in an inert gas or something like hydrogen. And particularly if you had a oxidation process, if there was leftover oxygen in there causing the disruption at the interface, hydrogen would certainly act as a getter, if you will, and suck it right out. And so we heated it up, and this, I'm condensing it, but Lordy knows when you do these experiments, there's so much of them are similar to Edison. There is the Edisonian approach, which says try a million things. And the other one that says no, you have to theoretically focus, and then when you have the solution, you test it. It's a compromise. You try and come up with even a thought as to something that might work, and you try that. So it's Edisonian and theory at the same time, melded together. If you go Edisonian, you'll be working forever. If you combine the two, you can cut it down to a limited number of tests and trials and so on. But still, it took a year until we finally got the hydrogen annealing and it got to work.
And you're saying you were working with Fred Hyman?
Fred Hyman joined, I guess, just about 9 or 10 months into the project. I would be going on for my doctoral degree, which required a period of 9 months where I'd be mainly away from the laboratories to get my residence requirement at the university. And so they began to Tom planned in advance to try and get somebody in the group so that when I left, it wasn't available for the full-time work, somebody else would be there to continue it. Mm-hmm. And that's how Fred joined the group. And Fred, very, very, very bright guy. I worked with him for many years, not just at RCA, but when I left in 1968, he came with me into the new company that we formed called Princeton Electronics. Subsequently, he went on to the Mars Company on vending machines. That's another story.
Okay.
It involves a Susan B. Anthony dollar.
Okay, we'll save that story for another time. So Fred came in, and you.
We were working on it, and we got it to work, and then discovered the horror of instability. It just wasn't stable, and so I focused on stability.
So that you got the transistor effect.
Oh, we got the transistor to work.
Switch,
it would work. It would switch.
But every time you turned it on, it was a different threshold.
If you turned it on, it stayed on. If you turned it off, it stayed off. It had hysteresis in the curves. The curve, instead of just going up and down, went up and came back in a loop. So you had your hysteresis loop, like just magnetism in iron, but the transistor, that doesn't make it workable. And so the question was, what was happening? We finally figured, of course, something was moving. Charge was moving through the oxide. What this charge was and how it went, we really didn't know. We had some theories about it. And we set about the problem of solving the instabilities, which went on for almost a year. And we were able to make them stable. We found that by doping the oxide with phosphorus, we could block whatever it was that was moving. It kind of was sort of a Band-Aid in the sense that you weren't eliminating what caused it. The thing was frustrating was that periodically you'd make a batch of them and they're absolutely stable, but you couldn't reproduce it, and which is obvious because you don't know what it was that got in and didn't get in. And it kind of leads up to the time Fairchild at the time was also working on it. That was the group I think was headed by Gordon Moore, and you had C.T. Saw and Andy Grove and Ed Snow. It was a very, 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 very good group, and we kind of had our little group at RCA Laboratories, so we could make them, and they worked very nicely, but they weren't commercial because they were unstable. Fairchild, and this is just before we did the phosphorus, by the way. Fairchild had solved the stability problem, but they didn't solve the surface state problem. At least they were having some difficulties with it. And we were planning, we were sitting in a lunchroom at RCA one day. One group of us, Ed, who was it again? Claire Thornton from Philco was there, a couple people from Bell Laboratories. And I said, why don't we start a small invitation-only conference? There are only about 60 of us in the United States working actively on silicon and its use in transistors, which is really amazing when you think about Silicon Valley now. Sure. 60 people in the entire United States working on that.
That's right.
And so I said, why don't we have a conference that's invitation-only? Everybody who comes to the conference has to submit a paper. There are no free rides, no free lunch here. Anyone who comes has to contribute. And maybe if we all get together for the benefit of everybody, we can interchange, and you give me some information, I'll give you some information, and overall we'll do better as a group instead of guarding our own little territories. And they thought it was a great idea, so the IEEE approved it. And because I kind of suggested it, I got to choose the venue where they asked me where I'd like to go. I said I thought Las Vegas would be good, which produced a lot of raised eyebrows, because I will tell you, nobody but the Elks and a bunch, that's the higher level, and it went down from there, were using Las Vegas for any kind of convention.
Sure.
And so I don't know who gave me the lead to the Stardust Hotel, but they were fascinated. A real genuine convention with real scientists was going to come to Las Vegas. They comped the entire group. They swept the floors. They were so excited at having a real technical conference come. We all know where that went. So that, I guess...
Did you have a name for the conference?
Yes, it was called, the name I came up with then was called the Silicon Interface Specialist Conference.
Okay, and the year was?
It was 1965.
65, okay.
That was the first one. Interestingly, I came across the, what do you call them again? Not the minutes, but the notes and the technical information on the conference is on the web. The IEEE has it. So I got the program schedule and the invitations. I was invitations chairman for the first conference, became the general chairman for the second one. But it was very successful. The people in the field came out, and a lot of information was exchanged. And I think the development of commercial integrated circuits was greatly benefited by this conference. I was fascinated too to find out it's still in existence. I Googled it the other day and found out, to my surprise, it's still being run, but not in Las Vegas.
There's still
anymore.
A few problems left to solve.
They alternate between, when you think about it, it's specifically the Silicon Interface Specialist Conference, that interface problems are so dominant, half a century later, is fascinating.
Just the
as much as you think
thinner.
Just they get more and more arcane.
Right.
So anyway, we're getting ready for the conference, and I get a call from Bill Webster, who invites me into his office.
And Bill at this time?
Bill is the director of the Electron Research Laboratory.
Okay. And Stanley worked for?
Tom Stanley worked for Bill, and I worked for Tom. And I'm trying to remember how the conversation began. He said, well, you know, Steve, he said, you're going to be going out there and we need some guidelines in terms of things you can disclose or not disclose. And to take that back just a little bit, when we got the transistor to work, Fred and I were very excited about this. And so we authored a paper called the Silicon MOS Field Effect Transistor. And we were going to submit it to the IEEE proceedings. I think it was called the IRE proceedings about then. It just had switched over. And what we were told was, listen, it's fantastic, the device is wonderful, it's been out, everyone's looking forward to the paper. What you must not discuss, because legal will never approve it, is how you did it. You can talk about the curves, how it works, how nice, it does this, make a circuit, stay away from the fabrication. And so we did. And we submitted the paper to the legal department at RCA, and it was rejected. And they called me down, and I said, why? They said, well, it's too sensitive. And I said, but there's nothing in there at all about how we made it work. And they said, Steve, you have to understand something. It's not how you made it work, it's that you proved it can work. Right now, everyone out there doesn't believe this thing is going to work. No one else is working on it. We haven't even announced it yet. The moment we announce it can be done, there are a lot of smart people out there. Once they know it can be done, they'll reproduce what you did. And they're absolutely right. I just happened to be the first because I'm very tenacious and I just didn't believe it would not work. But once you tell somebody else you see it can work, you can say, well, okay, let me go back to it. It's going to work. And so it was fascinating to me because it leads up to something that my whole life is very puzzling: patents. Do you file for a patent? Because I've been in technology all these years, okay, even up to right now today. When you invent something, do you patent it? Well, the problem is that to file for a patent, you must disclose how you got it to work. And that ran right into that concept, which is the damages telling people it does work. Yep. And so trade secrets, I think you might say, to me, have always been far more powerful than a patent. Even if you get the patent, which is very iffy, you've already disclosed the fact that it can work in at least one way to make it work. That's by regulation, you can't file for it. And then even if you do get the patent, you're going to have to prosecute it. Right. And so the net result is, commercially, a lot of damage can be done before you ever maybe recoup it through your patent in a lawsuit. And so the best thing is just keep it a secret. Anyway, that went backwards. Now where are we? Oh yeah, so now we're up to the Silicon Interface Specialist Conference. Right. And Bill Webster is saying, all right, generally, Steve, don't talk about how you did it, what the secrets are. I mean, everyone's going to want to know, how did you get rid of the surface states? And I said, yeah. He said, and there's also a problem we have about stability, which we know Fairchild has solved. Now he said, you have to understand something, Steve. We can't selectively give secret information to another company. RCA, I don't know the details of this, but had some big suit with Honeywell, I believe it was, back in the 30s or 40s, and part of it was an antitrust thing, had to do with some Honeywell patents, and truly I'm ignorant on this. But I know the net result of it was that RCA had to be very careful about disclosing things preferentially. Right. And the technical or the legal reasons are beyond my what do you call it, grade pay. So they said, on the other hand, we'd really like to know how Fairchild, got this thing to be stable, and they'd really like to know how we got this thing to work. And if I'm going to be talking to Andy, you mentioned something about, how to get it to work, we wouldn't be too upset, And he might just be saying something about how you get rid of the surface, how you get rid of the instability. Well, I don't know, he says, these things happen. So I found myself in Las Vegas, the first lunch break, we're out in the pool, and Andy is staring at me, and I'm staring at him. And so we kind of chit-chat a little bit, and I don't know who the first person was to say, perhaps it was me saying, do you have something you want to tell me? And he said, do you have something you want to tell me? And I said, hydrogen. And he said, sodium. Now, I tell that story, then of course, I tell that story to people who tell you that when you get someone to consult, for example, you pay them $1 million because he came up with an idea. That's a lot of money for just a few minutes work. Right. Those two words took millions of dollars of effort by teams. Of course. You can't make a judgment, and try and tell people you cannot make a judgment on the worth of an idea in terms of how long did it take you, how difficult was it to do, how many hours did you spend on it. It's what it achieves. Mm-hmm. So that's how things began to move along. Indeed, it was sodium. One of the things also turned out that does move was hydrogen. For the longest time, I did some experiments. I thought originally it was hydrogen, sodium in the same class, if you will, but I wasn't thinking so. I was thinking hydrogen because of all the water we were using, and the hydrogen anneal. And so I did some experiments with tritium and got to write a paper for the physical letters, the most technical paper I ever wrote. We did tritium radio tracer experiments, and in fact, we were able to see the fact that protons would move through the oxide. It was an interesting experiment because that material is extremely, extremely dangerous, but at the time, there was a reactor. Believe it or not, there was a reactor about 5 miles outside of the RCA laboratories. It was in the, I'm trying to remember the name, Grover Mills was where the flying saucers landed in H.G. Wells. That's where the reactor was.
Okay.
So that might have been built by aliens, except I don't know the true story. But we were able to prove that tritium moves, and that kind of disappeared. Do you know, I came across some articles recently, they're still working on it. They're using it as part of, it was rediscovered about 30 years later in the late 1990s. So it was nice. It does move, and in fact, they're using it for some type of advanced fabrication techniques now.
And you used it to prove?
I used it to prove that it was that protons were moving, but indeed sodium, which is next in the family, was the more dominant element. Both move, both will have the effect, but sodium was the thing causing the effect. Very, very large. And it's astonishing because you would think of oxide as being glass, which it is. Right. How does sodium move through glass at room temperature? In itself, it's counterintuitive, but it does. It's when you really think about it, it's amazing. The oxide is also interesting in some experiments that were conducted. I've never seen this published. It's also extraordinarily sensitive to low energy X-ray. We at Princeton Electronics, and it relates back to the laboratories, we were making a device which depended upon storage on the oxide to get an image. And what we found was the image would fade. And we thought that was due to gas in the tubes. And we pumped them and we pumped them and we pumped them. No matter how low we got it down, it didn't make a difference. And then somebody at Bell Laboratories said, Steve, take a look at the pattern. It's very diffuse. If it were a gas migration, it would be the areas that was being scanned and you were doing the ion generation would have sharp boundaries. If you look, the boundaries are very diffuse. It's X-rays. And to this day, I've never heard of anyone following up on the fact that something like silicon dioxide is X-ray sensitive down at 500 electron volts, which is astonishingly low. Sure. I mean, for X-rays, that's virtually non-existent.
Right.
So anyway.
So Fairchild learned how to fix surface states, RCA learned how to fix stability.
Right.
How long did it take the two of you then to come up with products that...
Well, products began to appear almost immediately. Even at the time we were talking, they were making individual devices. RCA was big into analog. And so the first home of MOS was not integrated circuits. The first commercial units were individual units. Right. And the success of MOS was elusive. Again, it goes back to Andy's endurance formula. If you think about it, it was in 1970, there was an article, which I have a copy of, that came out in one of the technical magazines saying, is this the year that MOS finally makes it? Total sales in 1970, I'll send you the article, total sales in 1970 were $14 million.
Yeah, I can believe it.
For the MOS devices, and it was not integrated circuits, it was all analog devices.
Okay. Yeah, Phil Ferguson sat in that chair a few months ago. Phil was the reluctant second CEO at General Microelectronics. Mm-hmm. So I have a lot of stories about the struggles they had with stability and everything else.
Oh, I'd love to hear them, really. That'd be fantastic. You know, there's so much, it's not just, it's nice to be able to tell everyone the stories here, but it'd be so much more fun and to read the oral histories of the other fellows that I work with. I came across Paul Weimer's, which was done some years ago, I believe.
On the IEEE site?
Yes.
That one, yes. I think I've taken a look through that.
Yeah, very, very bright, very brilliant man. When you really think about, if you look at something like the iPhone, and you were talking about the analog, half of the phone is analog, but when you look at the liquid crystal display on computers, that whole thing came out of a small group, in my opinion, at RCA. You had Paul Weimer, who developed the TFT, which is absolutely critical to lighting up the little cells on the computer screen. You had George Hallmeyer, who of course discovered the pneumatic phase in liquid crystals, that it could do it. You had myself and Freddie working on the MOS digital. Between those three groups, you had the basic core of what you see today is a flat panel TV display.
Sure. And you worked on an LCD watch.
Yeah, that was fascinating.
I'd like to get to that in a minute. Back up a couple of
yes, sir.
few years here. You talked about the paper that you were not allowed to give for the IEEE, but you did give a paper at some point with Hyman.
Yes,
right?
we did. We gave it at the
was
Electron,
that?
I believe it was in 62, 68, 3, at the Electron Devices meeting it was eventually, by that time RCA had announced the device.
I see.
In other words, RCA had come out in 1963, I believe, the first nice announcement. I could be off by the 1 year, but it was mid-63. Interesting article in Newsweek, not Newsweek, yeah, it was Newsweek, about, there was a column by Atherton Spillhouse. Do you remember that? Believe it or not kind of thing?
The name's familiar, but I don't remember.
He had a one-pager. And one of the things in that particular month's issue was the most. And it starts off, the tiny disk that Thomas Stanley held in his hands may prove yet to be the next revolution in computers.
Okay.
And it did turn out to be so.
Sure.
One of the few times something that was hyped as that. So that's, by that time RCA had announced it, there were releases going out, they had made the transistor available, and then we gave the technical paper that year.
Right. And in that technical paper you talked about this 16 transistor experimental chip that you and
During the
Hyman
paper, I
created.
believe we did, we focused mainly on, remember this is the devices meeting.
Right, okay.
And it's kind of interesting because there was a very definite pattern to how these things come along. First there was the materials war. Back in the early 50s. Is it going to be germanium? Is it going to be silicon? Is it going to be thin films? Then you got, once you began to home in on the materials, it moved up one level. You went from materials to the devices. And the MOS, even though it looked very promising, was only one of many. Shockley had now a new kind of 4-layer tetrode. Other people kept searching. It wasn't clear to everyone, oh, we have the device, let's stop. So you had the device wars where everyone, now that we knew what material was going to be, now everyone is arguing over what device is going to be the best device for the industry to pursue. And finally it began to home in on the MOS or on transistors, and then became the integrated circuit. It keeps going up by levels.
Right.
Then came the integrated circuit technology war. Was it going to be little chips being put on little metal balls like IBM was doing? Was it going to be something carved out mechanically? Was it going to be something on silicon? So the methodology of integrating it, how are the bonds going to be made? And it then, it went up to the large packages. So as anything, it grows. It grew first in materials, then it was a fight over what device, then how to integrate the devices. And there was a lot of interesting work on during that era.
And so you made this 16 transistor chip.
Yes.
That could be hooked up
It's
to...
a 16 transistor NOR gate, exclusive NOR gate, I believe.
Okay.
And it was functional.
Well, why 16? Why not 8? Why not 100?
Well, 16 for the is about the largest, I believe, that we could do.
Okay.
It was a number that produced an actual functional circuit that wasn't just a demo.
Yes.
It actually did something useful, if you will, and it had a moderate number of and it was funny because we would have loved to have put more transistors on it, but the failure rate was very high.
Uh-huh.
And this was something that always fascinated me. We would sit there, all of us around the table at lunch and at the conferences, and say, how many of these things do you think we'll ever be able to make on a chip? And people would think it'd be 100, and there might be some redundancy, maybe some way to make 200 and use 100. The concept, that original chip that we did was 1/4 of an inch by 1/4 of an inch, and I understand they get several million on them. How they do that boggles my mind. Really amazing.
Did you appreciate this was essentially the first MOS integrated circuit? Then?
Yes, it was.
Did-
No, we
did-
were.
did you
We were
you
very
knew what
excited and
you
happy.
were-
I think with the advent of that circuit, that's what I believe triggered the shutdown of Torkel's group doing work on the unipolar transistor.
Okay.
For a while, remember,
And these were P-channel transistors, probably?
those were, I believe, Torkel's were, I believe, N-channel.
Well, his were...
I'm not sure.
What were yours?
Ours were also N-channel. We made both. We made N-channel and P-channel,
P-channel.
but
Okay.
we stayed with N-channel. The complementary pair was to come later. That was Paul
Right.
One. That was actually not a clone over, it was a takeover of the complementary pair Paul had done way back with his thin film transistors. That we took that structure and ported it over. Remember, when the first transistors were made and sold, they were depletion devices. They were meant to be analog. In other words, they were normally on, you could shut them off.
Right.
Okay, the concept of turning them on as a switch and doing this in a complementary way was just a short time later. But your question was?
And, well, no, I was just trying to decide it was because P-channel were much easier to build than N-channel, at least here in the Valley for many years. So I was wondering what it was you started with.
Well, we started, I believe, with N-channel back in those
Interesting.
days.
Yeah.
If we produced, I'd have to go back and check, but I'm pretty sure all the diffusions we did with phosphorus for P.
Yeah.
And boron, I got it backwards, it's phosphorus N-channel. Boy, go back all those years. Could have been P-channel, I think it was N-channel.
Okay, interesting. And I've seen a page from your notebook that was signed by Woolmark and Ziniger of a new device new MOS device?
That was an attempt. That was an attempt. Yet that was the era of is there a better version of MOS?
Right.
And that device was basically a reverse bias diode with a gate on top of it to control. It was, if you looked at it carefully, the source and drain were two different materials, N plus and P plus, or N and P. Whereas in a regular MOS transistor, they're the same material, and they're bridged by the channel.
Right.
And this device was looked at as something to reverse bias and to control the breakdown. And it looked very promising when we built them, and I gave a paper out in Boulder, Colorado, and it was very interesting. This was, oh gosh, I think it was 65. I could be wrong. But it was again, the electron devices meeting being held in Boulder, and there was an excited announcement. I gave the paper on the device. Harvey Nathanson also had looked at it. He gave a paper. I'd gotten them to work, and I had all the characteristic curves. Harvey was pretty close behind me on that. We were talking about our experiences.
And this was Harvey who?
Harvey Nathanson.
Nathanson
of
from?
Westinghouse.
Of Westinghouse, okay.
The fellow who invented the DLP chip.
Yes.
That would be used half a century later by Texas Instruments.
Right.
Harvey also spilled 1,000 jelly beans in Germany, and I'll tell you that story some other time. It was at a conference like this. But
you were in Boulder, Colorado.
we're in Boulder, Colorado, and the chairman got up to say that a very exciting announcement for those of you here. Tomorrow at the end of the conference ended at noon. But for those of you interested, Bill Shockley has a great new revolution he's going to be announcing. He's going to be flying in. And you know, obviously we normally don't accept papers at the last minute like this, but it is Dr. Shockley, and it is a whole new device. And so those of you who want to stick around, he's very guarded about it, but I'm sure you'll enjoy it and it'll be great. It turned out to be the same device.
Is that right?
It was really sweet. He got up and he said, well, he gets his paper. He said, but already there have been 2 of them on it, and it's a little more than I have. So I just want to congratulate the people that did that, and it's wonderful. Nicest guy. That was really it. It just goes to the same thing. Things happen in parallel.
Yeah.
It's only a question of timing.
And you said at this time, was this the time in Colorado where you went out with Grove and Longo? And
No, actually that was, the driver was Bob Noyce.
Okay.
I'm sorry, Bill Webster was driving. Bob Noyce was sitting next to him. I was in the back with Bill. They brought me along because we were all very happy. We just had lots of happy hour stuff, and they wanted young blood in the car. So you can imagine how long ago it is that I was considered young blood. So they stuffed me in the back of the car, and Tom Longo was next to me, and this other fellow got this, and now there were 5 of us. And Bill looked around, and Bob didn't look around. Tom said, does anyone know who this fellow is? The guy was just sitting there happy. Nobody knew who he was, so they opened the door and pushed him out. And then we closed the door and we took off. We wanted to go for egg rolls. Everyone decided egg rolls at 1 in the morning and near Boulder, Colorado was a wonderful thing to do. So we scootled up and down the highways and made a couple of U-turns. Couldn't find the egg rolls. We did at one point stop off because somebody had to go to the bathroom. I'm not going to name a name, but it wasn't, I can tell you it wasn't me. Went in, didn't show up. We finally went in, passed out on the potty. We had to crawl underneath. Actually, Bill Webster crawled underneath and unlatch it so we can open the door and get the fellow out. So I thought to myself, this is a wonderful field. I love science.
Okay, so now we're up to about 66 or so, I think.
Yeah, 66.
And by this time you had your meeting with Grove and
Oh, things were
fixed
moving along.
the
The MOS devices had, I believe, and Dick Ahrens would be more knowledgeable, but I believe at this point had pretty much gone into Somerville, New Jersey, the semiconductor division.
Sure.
And
were you involved in the transfer of the technology at all?
just in consult. We were very close physically. We were out in
Right.
Somerville at all times. So yeah,
Okay.
we were involved. They came to the labs. We went out there. Very bright people. I think the fellow named Olmsted, Jack Olmsted, was the fellow that we originally worked with out there, who was our kind of interface on that device. For myself, back in the labs, I've always loved watches. And when the first, do you remember the old Bulova Accutron, little
Yes.
tuning fork?
Yep.
I was fascinated. I bought the one with the transparent face. I love to watch that thing and listen to it and so on. And one day, I think it was Tom, called me in the office and said, you know, George Hallmeyer. I said, well, I've seen him. And say hello. He said, George has discovered something very remarkable that's top secret. He said, there are 5 people in the labs. You're now the 6th one that even know it exists. And he said, I want you to go down and take a look at it. You know, only a limited number of people are being allowed to see this thing because of its impact. And there are people that we think might be creative in finding a way to get it to go. And so I went down to George. His was the only laboratory kept locked. You know, the doors to his particular lab bay were kept locked at all times. And so they invited me in, and George, I'll show you something. And he had this microscope, and he had these 2 glass slides on it, and a little battery sitting next to it. And he said, take a look through the microscope. So I looked through the microscope, and I'm looking at a glass slide, and I can see something's faint on it, but I don't know what it is. And he touches the battery, and all of a sudden, boink, there's a house a little tiny house, and he says, now watch. He takes it away, it disappears. And that was my first introduction to the first. That had to be the first liquid crystal display ever made in the history of the world. And it was fascinating, just a little house on a slide. And the problems, of course, at the time were that it's always the same thing. There are always defects until you perfect it. In the case of the MOS transistor, it was sodium, for example. In the case of this, we still don't know, or at least I don't know, what the contaminant was, but the liquid crystal would fail. I mean, to switch modes like that is it's very physically aggressive to do to material, and whatever else was in there didn't like it. And after
stir it all up over a period.
Something.
Yep. And
after a few days, it would turn brown. And so that was the problem they were looking at. Also, the response time. See, RCA, I started to mention before, had built its fortune on television. And even though they encouraged investigation in all these other areas, television was still their major interest. And flat panel displays, once color came out, and that was a massive undertaking. I don't know if anyone's ever written the story of the RCA one-year crash project to get color television, compatible color television. For a period of 1 year, they had cots. The scientists slept at the laboratories. They worked around the clock. Their families would bring food in and back and forth. The kitchen was kept open. It was a crash project because the FCC had given us 1 year, us being RCA, 1 year to prove that they could compete with CBS, or CBS, the method, would get the FCC sanction and be allowed to work. Mm-hmm. And so they had to create the phosphor. They had to come up with the idea even of a shadow mask. To take something from just raw ideas, they had to do the materials, they had to do the shadow mask. Everything was done in a period of 1 year. When you look back upon it, it was an astonishing period. I mean, to do that much in 1 year, it's like building an atomic bomb in 2 months from dead scratch.
Right. And again, we'll cover some more of this afternoon. And you were relating that to
liquid crystal development. So now, I love these watches. And what occurred to me when I saw that, I asked George, I said, how much power does this take? And George said, I don't know, we've never measured it. I said, does anyone have a meter here? And they said, well, yeah. And so we got a meter, and when he connected the battery up this time, we took a measurement. It was a couple of microamperes, which George thought was interesting, but not of great significance. I thought to myself, I had taken the battery out of my little Accutron, and it drew 10 microamperes. Yep. Okay. So now we had a display that was in range of that kind of support from a tiny battery, and the MOS transistor, particularly in the CMOS configuration, took almost no power at all. We could build a watch. And so I did some research for a week or two, and I got a whole bunch of financial reports about the watch industry, presented it to Tom Stanley. It was a $500 million a year industry, and we could do blah, blah, blah on it. And after about 3 or 4 weeks, the word came back from headquarters that RCA was not in the watch business. And by that time, I had built the first counter. George made me an 8-segment display, and I built a little decoder on it and ran it off of a crystal, and the numbers would change. Unfortunately, nobody took a picture of it, but that was the first it was the first liquid crystal digital clock.
So this was in
65, 66. Okay. And we filed for and did get a patent. And it's so funny. That patent is so old, it expired in 1987, which is really something. That's like 25 years ago it was expired.
Sure.
So I was very delighted to see that eventually it did take up. Watches began to appear. I'm not allowed to wear one. My wife thinks it's ugly. So parenthood doesn't count for anything when it comes to wearing a watch. Okay.
And RCA also was pretty heavily involved with the LED watch, didn't they? They built the chips for the pulsar.
Yeah, they were. That of course is Dick's specialty. But we were reminiscing. Right. First time I saw, we had heard about the LED. IBM. I'm not sure who had done the first ones, either IBM or GE. I'm not sure. But the fact that light could be emitted from a diode, they had tunnel diodes, so we knew people could do things with diodes and play with them. But this is the first time we heard about light being emitted, and so we got an excited call to labs that they think they had reproduced it out in Somerville, and so we all rushed out to Somerville. And they had this thing under a microscope. And in truth, when you biased the diode, it lit up red. Turned out later it was a piece of phosphorus that was stuck on it that was luminescing, but they didn't know it at the time. But it was good because it gave them this energy to go ahead.
Go find
and
out,
before they actually produced a real light emitting diode before they found out that the other one was a fake. They didn't know it. So anyway, yes, they've been in that. To me, it's just astonishing how far that's come.
Okay, so we're now up to 66 or so. So what anything else after the watch at RCA before you moved on?
No, I actually left in 68.
68, okay.
And so we continued to do additional work on MOS and work on the watch and so on. But the watch was the last active project I did before I left.
Okay. And what did you do in '68?
Well, 68 came. I decided to form my own company. That was the famous meeting that we had with Andy Grove down
Why don't you
in...
tell me about this meeting with Andy Grove?
Oh, okay. Right, it was before we were on camera. I really loved the laboratories. It was a difficult decision because, I mean, I enjoy what I was doing, but it's been 10 years. I kind of thought it might be fun to just try and start up a little company and see what I could do. And I had all of the naivety that's necessary when you're, in your 20s to make you think you can lick the world kind of thing. Yeah. And so I submitted a notice of resignation and left in 1968 and formed the company. And before I did, I'll take you back again. This was now it was either 68 or, yes, it was a 68 meeting in Washington, the Electron Devices meeting. And Andy Grove came up and said, Steve, what you doing for lunch? Gordon and I would like to have lunch with you if you have time. I said, sure. And so we sat down at lunch, and Andy said, listen, after usual pleasantries, he said, I want to tell you something. He said, what I want to tell you, I can only tell you because you've already told RCA that you're leaving. Otherwise, I would not even speak of this. Separate and aside from that, we'd really appreciate it if you could keep it just confidential for the moment. There are very few people that know about it. And I said, well, okay, what? And Andy said, Gordon and I will be leaving Fairchild to form a new company. And Bob is coming with us. We're going to be financed by Arthur Rock. I don't know if you mentioned the name Arthur Rock at the time. We have financing. It's a brand new idea. There are only about 6 or 7 of us right now. And we're not sure of the timing, and we don't even know what we're going to call the company. But we'd like you to think about joining us. And my initial reaction was, well, very flattered. Thank you, Andy. But I was kind of thinking of, running my own thing. And Andy gave me once again a wonderful piece of advice. He said, let me tell you something. I know you're excited, you're young, I'm a little older than you are. You're going to go out there, you're going to run your own team and so on. He said, Steve, there is nothing more powerful than being a member of a small team and working together as a team. You can do infinitely more than working by yourself. You want to think about that. And we've worked as a team. For many of you, you've seen what we've done. We'd like to have you join that team. I think you'll find it very exciting. I said, it actually does sound very interesting. Let me think about it a bit. They said, well, what's the schedule? And I said, well, the conference is over tomorrow. I'm flying back to Princeton. And they said, well, that's coincidental. We're going up to Bell Telephone Laboratories. What we can do, we fly in is stop off in Princeton at your house. I gave them the address and everything. And we can talk about this some more. And I said, sure, that's a great idea. Well, the next morning came. And my wife decided, first wife at this time, not current wife, first wife, decided she wanted to stay in town and do shopping. So we did. We stayed one more day, flew back, and when we got home, there was a business card. Gordon's card was in the door of the house, and a little note on back said, Steve, give us a call. We want to talk to you. And I didn't return that call, and so here I am now. I read somewhere else. Marvelous people.
Did you have any other contact with Andy or Gordon over the years after that?
No, I think we may have had telephone contact several times during the period after that, but no, not really. I followed his career with great interest. He's a great man.
Certainly is. And so you went on with your original plan to form your own company?
Yes, we did. Formed the idea I'd come up with, actually when we first formed the company, the first thing we would try and build was something that it was a radical idea. There was a device called an area optics. It would generate a pinpoint of light. You've got to remember, before laser diodes were well known and were used. I think they had light emitting diodes, but I think it was a while before there were lasing diodes. And so the light beam itself was so small. Let me back up and give the introduction to it. One of the other projects at RCA that I did consult on, very powerful, was the video disc. And the whole concept of how to do a video disc. There were 2 different thoughts in industry. Actually, RCA Labs itself, it relates. If I get off subject, just stop me. But RCA, again, back in the video world, was trying to find some way of doing video more than just a high-speed tape. They had demonstrated videotape by just taking audio tape and running it at about 300 feet a second, and it produced video. You could do any show up to 90 seconds, and it was wonderful, but that was kind of a limiting format. So they were working on it, and there were 2 different approaches. One fellow was working on using holograms, and his name escapes me right now, but what he was basically doing was he would shine a laser, and they were able to record video as a series of holograms on a rotating disc, which is interesting, but in order for that thing to be practical, you had to have a color camera tube. The whole thing had to be built for $400. That was the magic number. And there was no way at that time that a $400 camera tube in color was going to be developed. The other hand, there was something called, and this was Tom Stanley's invention. Tom came up with the idea of using RCA's really, I would call it advanced technology, their know-how in technology in pressing vinyl discs. We had an enormous record pressing plant in Bloomington, I believe it was, Indiana. And Tom had come up with the idea of basically going the route that they did when they went from the 78 RPM to what was called the microgroove. That's how you got a 3-minute disc to be a 1-hour disc. Tom was looking at the next generation of that, where you'd be able to put 25 grooves in a single groove of a microwave record. That's how tiny it would be. And it was fascinating, because if they could be made to work, RCA had the tremendous facilities to make them. And pressing a disc is cheap. Everything else would have been more expensive at the time. And so a lot of work went into developing the video disc, which in fact ultimately did get on the market for some period of years. But there was tremendous challenges. The biggest one was how to get a needle that was fine enough to get in the groove and then keep it from touching the walls of the groove. Because if it ever touched the walls, the way it did on an audio disc, it would destroy it. The grooves are too fragile. And they actually created a tone arm. To me, it's just amazing. They used a feedback circuit. The needle itself never touched the walls of the groove. It was held exactly in the middle by 2 little magnets. And there was correcting currents, little electromagnets. And if the needle started to veer towards one wall, it would be pulled gently back to the center. And that got to be working. So that was a huge feat. They could actually get a needle, keep it in there, and there was no wear on the grooves. What kind of fascinated me was why they didn't take this and apply it backwards to long playing records instead of wearing them out, wearing out the needles. To me, I always thought it would have been a great idea to have used that piece of technology just for the long playing discs in terms of maintaining their quality. But anyway, didn't happen. So the next problem was the disc had to be conductive, the surface had to be conductive if the capacitance variations that the needle didn't actually wiggle, it went up and down.
Okay.
And so the guide, it didn't go up and down. The needle could not be allowed to move because the signal was being embedded by an undulation in the base of the track. And so the needle was kept perfectly centered if it started to move, whereas the signal was in the undulations. And again, this too is necessary because on a standard record, it's lateral. Right. And the fineness of these grooves was such that you couldn't, that was a waste of space. So they flipped it. Instead of the variance being horizontal, it was made vertical. The problem they needed now was to get the surface of the disc conductive, because it was the variation in capacitance that would cause the signal to be generated and create the video image. And after a lot of experimentation, they did this, I believe, with a very light flashing of copper. And it looked good, and it played, they tested it, it was fine. They put it into production and actually began to sell the discs, and then something funny happened. All the copper started to fall off the discs. So they had themselves a product, literally something out in the marketplace that had life problems. And they did kind of resolve that one, but meanwhile, the laser disc, I think 3M popularized it, but the laser disc, which went the next step further, became the dominant source, and eventually to be made into the little CD-ROMs and DVDs. And all of this is a prelude to what I thought I wanted to do when I formed Princeton Electronics. At that time, I knew about the audio disc, or rather the methodology they were using to do the video disc with the mechanical thing, and I'd come across this very fine optical needle, if you will. It was a device made by a company in Long Island called Airy Optics, and it wasn't coherent light, but it would focus a very tiny, I think it was a 4-micron beam on the surface. And my great thought was that somehow I would use that to make a really small audio record, which turned out not to be what I did. About a month into that, when we realized the problems, I had another idea, which came to me about using these.
Now you had founded Princeton by this time?
Yeah, Princeton Electronics
existed?
Yes, it existed. Yeah. We were about a month into trying to do it. At that time, the company was 2 people, myself and Bob Persing, a technician would work with me, operating in my garage, which is always a place you must start. I was offered a lavish 25,000 square foot building, but I said, I have to start in my garage or I don't have a story to tell later on. Right. So anyway, we were working on that, and one I was kind of sitting there, and one of the problems we had in the storage, in the silicon, there's this thing called the silicon Vidicon that everyone was working on. This is before George Smith came up with the bubble technology that allowed you to actually make a camera out of just a disk of silicon. So what you had was a disk of silicon being used as the light sensitive target, but we didn't have the wiring capability to get in and interrogate the individual cells. So it was a hybrid technology. An electron beam was being used to scan the disk. And if you will, that gave you the ability. And one of the problems that they had was on the surface of the disk where the diodes had been created, there was oxide. And the oxide would pick up a charge and would block the beam so the images would fade and the camera tube didn't work so well. And I thought to myself, after those guys, about 2-3 months after we left, you could put an image on the oxide. You don't need the diodes. You could store an image. And so I sat down, we filed a patent on it, which we ultimately got, on using a silicon target to store the information for an image. And again, it comes down to memory, and it fascinates me. The tube was very successful. We created a whole bunch of stuff. We did the first airport X-ray systems for Picatinny Arsenal. They actually, the Lithicon, which tube was called, would store one frame, high resolution, black and white TV. That's it, just one frame.
And it was, the image was stored in an analog?
No, it was, yes, you would say, it was stored as a charge pattern.
Okay.
If you picture the target was a very simple one. It was a silicon layer was grown, and we etched into that a grid. And so you had a grid. Now when you brought the target up to a voltage, the beam would penetrate and you get your signal. If you charged the oxide, which was an effect that was inadvertent in the Vidicon, the charge would repel the beam, and so if you charged this part of the oxide, the beam couldn't get through, and that'd be black. And if you didn't charge the other part of the oxide, the beam could get through. In other words, you were storing an image. And so we wrote the image as a charge pattern on top of the oxide. And as long as that charge pattern was intact, you had the image stored. Things like gas and other things we talked about, X-rays, would make it fade, but at least you had it for many minutes.
And you had to read it out somehow.
Yes, it reads out just the way a silicon Vidicon would read out. You're scanning the surface, and the signal comes out of the target as a variation in signal because it's monitored. In essence, in a Vidicon, you're recharging the diodes. In the image tube, you're just looking at the charge that's on the oxide. And so you literally get a high-resolution image.
And the benefit of this over the previous methods?
Previous methods
power,
were, biggest thing was the relative inexpensiveness, the quality of the image, and the fact they could do grayscale.
I see.
There were storage scopes at the time, for example, but they were binary. I think Hughes Corporation made a number of storage tubes that were primarily binary, and they were being made for things like radar retention and so on and so forth. This tube had grayscale, and it had high resolution. It was the equivalent, I remember thinking at the time that, wow, it effectively is storing something like, including the grayscale, something like 10 million bits of information, which is phenomenal. It'll be a long time before we saw 10 million bits of memory in semiconductors.
CCD or something, right?
Nothing stands still. So we came out with a tube, which we put in a device called a scan converter. All the scan converter was a box that said basically you can paint a pattern any way you want on this image and then read it out as a TV signal. So it's a scan converter. It converts something, any kind of electronic image, any kind of signal into an image. And it was they often say, it was a fantastic solution to non-existent problems.
Yes, my next question was, okay, so who wants this?
Well, the first breakthrough came actually with, I'm trying to remember, was that ultrasound medicine? No, a whole series. We advertised it, we began to send them out. We got calls from various companies interested in the fact that we're using storage tubes or interested in using it. This was like a whole next generation. And one of the customers who purchased it was Picatinny Arsenal. They liked it, and they gave us a contract to produce with them a portable low dosage X-ray system. And the original purpose was for battlefield injuries. When they had a medic going out in the battlefield did not have a means of telling if someone bone fractured or not fractured. And what they needed was a portable X-ray unit that was not dangerous and would allow the guy to see, is this a fracture, not a fracture? And the technology itself, or the system itself, was very simple. They had already developed a flash X-ray tube. This is a tube that just goes pop. It develops one blast of X-ray. The total dosage is very low. It's very intense, but it's low. So it's harmless, if you will. They would get a photoluminescent screen, and so if you put an object in front of the screen and you pop the X-ray, the screen would flash up and then the image would disappear. So now the challenge became one of how do you maintain this image?
Store it.
And that's where the storage came in.
Okay.
They took a sensitive camera, so you popped the flash that made the image, the camera picked up the image, put it into the Lithicon tube where it stayed. So the illusion, if you will, you popped it and then you could see an image and study it.
And how long did it stay?
Oh, the image would last for many minutes.
Okay.
More than adequate to know for actual practical use. And so that was very successful. We were not allowed up to the demonstration, interestingly, because there were a whole bunch of government agencies up there that we weren't allowed to be with, like, whatever you want to call them, NASA, the NSA, and CIA, everyone was there to look at the tube. But out of that one meeting came a lot of opportunity. For example, the FAA purchased the unit. Actually, didn't purchase, they sent out an RFP to 3 customers that were using it, using our stuff. I think Phillips was one of them, American Science and Engineering, and Bendix. And they decided they wanted to try to see if this technology, this little flash X-ray unit, could be used for security purposes. at airports. And so the first airport, you want to talk about irony, the first test ever was at the airport in Oklahoma City, later to be that huge, horrible bombing.
Yep.
And I have the original report, which I think back in the day was confidential, but it's long since been declassified. And it was very fascinating. Some of the stories that went along with the test were very funny. They were told at the gate that there would be, what's the word? Not stooges. There would be people secretly being set up to be bomb makers. Old ladies, you would never know who they are, and they'd hide a dummy bomb in their clothes. And the question was, can you pick them up? Can you find them? And so everyone was on a hair's edge because of the value of the system. And remember, 3 systems were up in shotgun tests, and all of them want to get these phantoms. People coming through, they wouldn't know who it was. Don't even judge them by how they look, because they're not going to be picked for anything but looks. They may be carrying a bomb. And so this little old lady comes up to the Bendix system, and hands a package, and they put it on there, and holy smokes. On the screen, there are the sticks, the logs, the sticks of dynamite, wires running all over the place, batteries and gears. And they grab the old lady, who was obviously a plant. Right. They hustle her into a room, and they grab this thing, and following protocol, they take it, and they dump it in a bucket of oil. You don't use water, you use oil. And this woman is crying and crying and crying. Turns out, when they open it up, they've managed to destroy a toy truck. It was a logging truck, and it had the little logs on it that looked just like sticks of dynamite, and it had the batteries that ran the motor, and it had all the wires and the requisite, except this was just a grandson's gift. That's one of the more humorful stories that came out. It also was used by the Library of Congress. They have a tremendous problem in book theft. And they've tried, of course, these days you have all the things you can put in books, but the problem with that was there are 10 million books, and the thought of pulling 10 million books off the shelf and putting a sticker on them. So they did purchase a unit. We also sold a unit which turned out, end up in Jordan for King Hussein's personal security. And it was interesting, we found out about this only because the unit failed. And so we got a call from, the government is so funny. We got a phone call, I can't tell you who I am, but we need to bring a unit back that you sold. It was some nondescript, we had sold this to some nondescript government company or something, we didn't know what it was. And we said, okay, well, how do we reach you? You can't reach you, I'll call you, someone will call you and give you a phone number and you call back. So we make an arrangement. The unit appears at our door along with 2 very burly, swarthy men. And I said, with these, they will be at this unit at all times. That's their job. They did tell us that this unit was being used in the Mideast. We found out later it was the same. These were his personal bodyguards, and their instruction was that unit was never out of their sight. We couldn't keep it overnight. They had to make sure nobody was sticking a bomb in the darn thing, I guess. And so we worked on it the first day, found out where the problem was in the supply. We started to get the parts together. Then they had to take the unit back to their motel, and they brought it back the next morning, and we fixed it, and we would go by, and they took it back. And I guess it worked because King Hussein was never assassinated.
That's right. You never heard from them again.
No, we didn't want to hear bad things.
So how big did Princeton grow?
I think at our peak, we were bringing in revenue of about $3 or $4 million.
How many people?
At that time, it was about 30 people.
Okay.
And like anything else, our technology was, we didn't have the kind of revenue explosion. Part of the problem was we were an OEM. This is something that I've always kind of taken as a lesson to be learned. When you're an OEM, the power of it is you're making this device and selling it to everybody. Right. Okay, anyone can buy the device. That's great, because now you have a big market. Whereas if you you're lined up with a particular client, or you then follow it through to its actual use, you're a more limited market. The problem with being an OEM is that you're really selling technology. And as we've all found out, even back in those days, technology moves along. Yep. What was laughable when we formed the company in 1960, it's like, oh God, there'll never be a 10 million bit semiconductor memory. Oh yeah. Our units, we went 10 years later after that, 1978, I went through Zurich, Switzerland. They still had one of our scan converters in operation on one of the X-ray systems there. So they had a good lifetime. And eventually the MOS came and bit me in a tushy, as they say. They started to make big memories, and of course you didn't need the lithicon tube anymore. Sure. But it was fascinating. If you remember Super Bowl, 1969, 1970. Super Bowl was the first, during the middle break of Super Bowl, the first pictures from Mars was Mariner 9. Okay. Coming back. They were being assembled on a lithicon tube out in California in a trailer, and then beamed out over the networks. So there was just a tube. It was nice to know that tube was the link between Mars and the vast audience we had here. Sure. Oh, last one but not least, ultrasound medicine. Interestingly, the first grayscale ultrasound medicine was done by the University of Chicago. They had been working for a long time on this using scopes, and they had switched over. They used our tube, and were finally beginning to get diagnostic quality images. The problem was the mode they were using it in took a lot of care in how you scanned it. And then a fellow I had gone to school with back at Cooper Union. A fellow named Ralph Rinaldi called me from California. He was working for a company called Rohe Scientific, and they wanted to get into the ultrasound business. And he thought the tube would be wonderful. But Ralph had a great idea about how to paint a picture that made it easy. In other words, it was done by target modulation. Without getting technical, it allowed the picture to be scanned in and then it would be stable. If you rescanned it, it stayed. Whereas the other way, as you were scanning it, it got brighter and brighter. And so you had to be very careful how you scanned it. This way, it gave you almost like a real photograph. And so we began to sell these units, and Rohe Scientific came out and began to sell one of the first of the medical ultrasound systems. They were followed by company Unirad out of Colorado, again, using our stuff. So our main revenue during that period was actually ultrasound medicine. We created the first units. They went into the field. They were enormously successful. Our competition there ultimately ended up being Hughes Corporation, who several years later began to try and compete they made storage tubes as well. Mm-hmm. And they were a very effective competitor, unfortunately. But between Hughes and between the fact that our technology was stagnant, we didn't have this is, when I began to appreciate Andy's advice. The company was very definitely sustainable, but it was built on a technology, and we didn't have the resources to move the technology forward into the next level. And so eventually, we got superseded. But by that time, I had sold the company, done nicely, and moved on from there.
What did you move on to?
A premature retirement, I think. Mm-hmm. I thought that was really wonderful. I came up with some fellows, and we did some very interesting stuff with Hahnemann Medical School University on continuing medical education.
Sorry, which school?
Hahnemann Medical School and University down in Philadelphia. And so I got involved for a while with some people in continuing medical education. And about, I guess it was 1989, moved down to Florida and formed a company called Ascot Technologies, Inc. and decided to do something because there was a lot of excitement out there still. And came up with the idea of applying expert system technology into some business applications and doing some advanced work into OCR and so on. And that's the company that I was with right up until 2009 when it was acquired.
Where did your background in expert systems come from?
Books, learned it.
Okay.
It's like anything else. You take what exists and then you modify and advance it to take it to the next level. Mm-hmm. I didn't invent by any means expert systems. They're part of artificial intelligence. But their primary use was in areas, they're very different from a rules engine because they infer. They use, let me take a second to tell you. A rules engine does rules. It always does the same thing. An inference engine, which is the core of an expert system, makes inferences. It's never 100% right, but it's good enough to mimic an expert, which if you're right 98% of the time and 99% of the time, it's very, very commercial and very feasible. And so the first area we went into was that of insurance tracking, and that was in 1999. We had already put a whole bunch of systems out in healthcare. Do you remember the HCFA form?
No.
HCFA stands for, it's the bill the physician sends to the government or the insurance company for payment. It's a standardized form. It was being made with dropout, meaning it was made with red ink. And so the form was very suitable for OCR. And OCR, which is very interesting, it all comes back to memory and computers. OCR back in 1980s, late 80s and 90, was done on something called a line scanner. In other words, you had special fonts. You would run it through a very complicated machine that would look at the font and identify what it is. The problem with that technology was that if there was an error, even one error on that entire form, and paper had to be pulled and worked manually. And so the judgment of a good OCR machine then was how many documents remain untouched. What people didn't anticipate was imaging. Imaging came along and changed the whole game, because now for the first time you could actually generate an image of the document and then electronically work on that image rather than try and pass it through a line scanner, and it would work on anything. The problem was there was no open architecture software available. Until 91, a company called Symbus up in New England came out for the first time, and remember, computers were still just developing and personal computers were just coming on the market. They came up with open architecture software that would run on any computer, and would allow you to do OCR on an image. And that company too became, I guess, a casualty of technology over the years. But we got involved with it, I got involved with it in terms of building systems, and we did a lot of them for the medical field. Blue Cross Blue Shield of Memphis, for example, United Healthcare down in Florida, in Coral Gables, which is very interesting. United Healthcare at the time was called CAC Ramsey. It's a company founded by a very brilliant Cuban immigrant. And when United Healthcare bought it, they didn't like it the way it was organized. I'll explain what I mean. Culturally, most of the people working in healthcare at the time were women. And so you had this open room filled with women who were just chatting away with each other while they were working, chatting away, chatting away, chatting away. And United Healthcare said, this is not good. You know, we have to stop it. So they passed the word, stop them. But you don't tell a bunch of happy women in that ethnic group not to chit-chat. They're going to chit-chat all day long. They do their work, by the way. But United Healthcare is a big organization, and there are standards and there are models and so on. So they put in barriers, which was a disaster, because now the woman stood up to talk. And when they stood up, then they couldn't work. At least without the barriers, they were sitting and talking and working. Now they were just standing up and talking. So that barriers came back down again.
And physically, what was your product? Was it
the
box?
product was software.
Roller tape or
Right.
whatever.
The product was software. And just take a little bit further. 1999 comes around, and we have done something a little unusual. OCRing a form at that time required that you have a template. You know where everything is. In other words, up here is a policy number, for example, and here is a doctor's name. You know exactly where to go on the form to get the information. Well, we had begun to develop a technique where you didn't have to know where it was, and in fact, you could do it on any form, which meant if you wanted to go for a policy number, you look at a form, and you say, well, how does a person do it? Well, you look and you see there's a word policy number, and numbers on the right, or sometimes it's underneath. So what we're going to do is we're going to look for the label, then we're going to scour the area and find something that looks like a policy number, and that's probably it. And so that was the beginning. The concept here was now you're beginning to build software that thinks like a person, and you emulate what a person does. And so we're starting to capture these elements. Now something even more interesting came along. We didn't know it was an expert system yet. It was now just a better OCR system. It was using a more advanced technique to locate the position of the element, but other than that, it was still pretty much just simplistic. Find a label, look for something, and so on, which is not trivial, because for every time you think you have it knocked down, another form comes out, and it ain't where you think it's going to be.
Right.
So we're contacted by a company called American Security Systems, later to become Assurant, which is a giant in insurance in the United States. And this was back in '99, and they had heard about the fact that we had this form, we were doing something with title forms with attorneys of title insurance up in Florida. They being American Security Group, was one of the top 3-tier trackers of insurance. Have you heard of insurance tracking?
I've heard of it.
Okay. When you take a loan out on a house or a car, okay, you have to get an insurance package on it. And you'll notice whenever you get a renewal from your insurance company or a cancellation or a reinstatement, a copy of it went to your lender. But it doesn't go to your lender. It goes to a company that's tracking the insurance for the lender.
Okay.
And if you examine a lot of the forms that come out, they're all going into Springfield, Ohio, which is where Assurant, or at that time American Security Group, had a tracking facility. And so we went out to visit it, and it was fascinating. They are in the top 3 tier of insurance trackers, which means they write their own insurance. The other 2 were Balboa and a company called ZC Sterling. The 3 of them accounted for 90% of the insurance tracking on mortgages in the United States. And the problem they had at Assurant, or American Security Group, was they were losing market share. And the reason they were losing market share was because the other companies claimed to have a better technology. So that means they had imaging. And the clients that came in, who were very non-technical, looked at this imaging facility and said, well, that's advanced. And then they looked at Assurant, and all they had were these women in front of these old Unix terminals on a green screen, typing away and looking at paper and typing away. And naturally they assumed that the advanced technology was better. And Assurant said, actually, it's not better. It slows them down, but it gives the illusion of being better. And we need something that is better. And we're not going to put imaging in. We need real OCR automation. And they said, well, why a little company like us? Well, it turned out to be interesting. They being the IT department, a very large IT department, had apparently been trying to do this for several years, had spent about $3.5–4 million, and it failed. And so when they found us, the IT people said, listen, it's not going to work. You being the marketing people, you want to pay for it, that's fine. Keep these people away from us. Don't even ask us for any help. And it was interesting because that was a lucky break. Typically when you go out and you offer a solution to a large company, their IT group blocks you because their job is to generate the solution. Your job is to give them tools.
They're the gatekeepers.
That's right. They're the gatekeepers. And in this particular case, they had tried it and failed and were convinced it couldn't be done, so they didn't care. It took us a year and it really started to work. But the first thing about it that was interesting, you talk about expert systems, well, when I stood there watching the operators, I realized, holy shit, this is not data entry. These operators, I said, how long does it take to train them? Well, you see, this is a certain form from a certain company. Now, that policy number means a certain thing. If you see that policy number, then you got to go here and get that, because that language doesn't say replacement cost, but it means the same thing. So the training for these people, it took an operator like 6 months of training to begin to understand the form enough to make the knowledge-based decisions about what to do with the data, what data to take, where did you find the data? Maybe it didn't say policy number, maybe for this carrier it says account number. And so we realized this is not so much data capture, this is knowledge work. And we started to build a knowledge base with an inference engine, and that's an expert system. When people would ask us, what can it do? The answer is very simple. Anything that a trained operator can do. What it can't do is artwork, and I'll explain. Standard story I would tell. The things that it can't do are as follows. You have a submarine sonar system. You've seen them, these hash screens with everything dribbling down, just like in the Matrix. And you'll have these unique people who can look at that screen and say, that's a submarine and that's a whale. And then you don't see anything. And another guy sitting next to me says, well, I see two shapes on there, but I can't tell the difference. And the third guy sitting there saying, what? I don't see anything. That part of the brain you can't do with an expert system. That kind of recognition it's like music. It's in a different side of the brain. It's on the right-hand side of the brain. It's in imaging. You can't touch it. The other side of the brain that's analytical, you can. So the rule is, if you have a trained operator and you train them on the manual, you can put it in the manual, you can build an expert system to remember everything. And what's more powerful about it is it combines the knowledge of all the operators, and it gets better and better and better. So anyway, Assurant came out with it in 2000, went from 15,000 documents a day back up to 120,000 documents a day. Today they do 350,000 documents a day through that software. In 2003, they acquired, 2003 was interesting. We have been working with them for 4 years. And they had paid us some very large figures in licensing fees for the software.
And we, by this time, how big was your company?
ATI Systems at that time was 8 people.
8 people, billing of roughly?
In the millions.
Okay.
Nice.
Sure.
I'll tell you my problem is why I never got to lead a big company. I could never get away from the bench. I've been criticized, rightly so. Princeton Electronics was financed by Roussel-Clough, among others. Roussel-Clough was the largest French pharmaceutical maker. And they became interested because, again, our imaging tube technology enabled people to see fragments in injectables. I know I'm going back, and you can edit this out later if you want. But one of the customers we had was Shearing. Shearing had a problem. They make injectables. And one of the things that's dangerous in injectables are particles, because a particle gets into your bloodstream, it can cause a clot. And so these are being examined for particles. And the way they examine them is operators sit in front of a table that has an illuminated plate, and they take each individual vial, and they spin it, and they look at it, and it passes, spin it, nope, doesn't pass. And they do every single one is 100% examined by a human being. And Shearing wanted some way to automate it and to make it, less subjective. Well, we developed a way with the tube, operating in dynamic mode, which basically showed only moving objects. It would look at a scene, and if something moved, you would see it moving, but if it was stationary, it wasn't there. And so we'd spin the bottle, and boy, the thing lit up. You could see all these fantastic particles swirling around. And that was the problem. It was too good. Every single vial failed. It was too much better. And so the bottom line was it was never put into production because everything would have failed. The other interesting thing is they would tell you that realistically, it's all show. I said, let's assume you have a glass vial with nothing in it. Now you snap the neck off. What do you think just happened to all the little pieces of glass you created? Do you think some of them may have fallen into the liquid? Of course they do. But it was cosmetics. So we were financed by Roussel-Clough, the pharmaceutical company, to develop the machine for them, which we did. They ran into a similar problem. But one time, their expert, the fellow who had taken us over there and introduced us to the 2 brothers that ran the company, came over and visited us in Princeton. And I was sitting in the laboratory working on a problem we had in the lab area, working a problem we had in getting the tube to focus in the corners. And he came over to me and he said, "What are you doing?" I said, "I'm working." What at work? I said, "I'm working on the board." He says, "You're the president of the company. You shouldn't be in this lab. It's ridiculous. You need to be in your office and organize the company." And he was absolutely right, but that was my problem. I could never get away from the bench. Even the company I had now, which met with success, was because I never got out of the technical part of it. I'm not a great businessman, but I had a lot of fun with technology. And overall, I'm a lot happier because I've always loved this stuff for all these years.
Right.
So I'm doomed. Andy was right. I would have been so much better with those guys helping me.
With the team at Intel.
Absolutely.
And I interrupted you when you were telling me about the number of documents that were being read.
Right. They had gone up to about 120,000. So now they had an interesting point. They came to me, this day being Gene Mergelmeyer, who at that time was the vice president of marketing for the company and who had sponsored the project, and said, look, we need to be independent of you. We'd like you to think about giving us a source code license, because up to now, they had the object code, but we were the ones that had the source code, and they had no rights to the source code. It was kind of interesting. Well, a second. Turned out what their problem was is they wanted to go public. And the underwriters told them, hey, the software that has made all the difference in the world that you're using and showing everybody,
And you have
and
no
is
control
on record,
over.
is being made for you by a tiny company that you don't own, have no control over. We're going to have to put that in the prospectus. And that ain't going to fly. And so they came and they said, well, look, we'd like a source code license. We gave them a license, or sold them a license. Again, it was expensive for them, but it allowed them to maintain the software. We also kept the right to audit them once a year to make sure everything was in order. And basically, they just used it as is and have for many years. It's very powerful stuff. But once we had done that, we were locked out of doing mortgage, because part of paying us for the source code with a lot of money was they had exclusivity for 5 years. And so we turned around and said, well, what other than mortgage can we do? And then it's automotive. And so in 2004, we began to develop the same expert technology for automobile tracking, which is similar but somewhat different. We're very successful with this. Partnered with a company, introduced us to some of the big titans, and in 2009, we had the same problem all over again. The company we were working with, a company called Southwest Business Corporation, is a company out of Texas, and they were doing automotive tracking, and were getting ready to get into the insurance world, the mortgage world, and suddenly had the awakening of, once again, this little company controls the technology. What are we going to do? Do we take the giant step? Do we cut ties with them? Well, I sat and I talked with them, and I think they made the right decision. They purchased our company.
I see. Okay.
And so on that fateful day in 2009, after 40 years of being an entrepreneur and a businessman, I became an employee. Now, I had been employed for a long time under my wife, Karen, but this was officially for a big company. It's amazing when you're employed by your wife, you pay for the privilege. That's even more fascinating.
There you go. And the company, you changed the name?
Where the company at the time, once we reformulated back in 2004 for the automotive industry, and we changed the name to Cognisys.
Cognisys, okay.
And Cognisys was then purchased by SWBC, so we're now a division of SWBC, which is a fantastic company, unbelievably great.
And you're still going into work every day and running the company? How big is it now?
We're still in Florida. They've kept us in Florida because they kept the company core in Florida.
Sure.
We now have, we've expanded to be 6 people, which is really a joke because we were 8 people, now we're 6 people. Well, we have the support of a huge company behind us. So a lot of the more, I won't call it medium, but a lot of the more basic stuff has been ported over to Texas and stuff like that, and we concentrate on the core of development. Getting to it's fascinating what's available out there. Now that, and again, remember I told you the problem I had all these years with Princeton Electronics were you're running your own little company, you don't have the resources to expand, get into markets. And so you've had this technological breakthrough and you live on it, and you live on it, you live on it. And truthfully what we're doing in the field of data capturing, if you will, or expert system technology still has not been surpassed, and it's been a long run. I mean, we started doing it back and successfully, commercially, in 1998, 99, and we're still doing it. So it's moved along. But on the other hand, what excites me so much about, and for the first time being part of a team, and Andy, yes, you were right, is that there are a lot of smart people in a company going out and opening up marketplaces. So somewhat belatedly, I am now an employee of a very smart team.
Are there new areas that you're looking in to apply the technology that you can talk about?
I can't.
You can't.
No, that's one of the things that happens.
That's fine.
I'm back to the I can't say.
Sure. Okay. How about, do you have any life outside of the fun at work? Do you have hobbies?
We had great fun. We had great fun. We had a lot of fun when, I'm trying to think of the best way to describe this. One of the fun times, for example, was back when we were financed by Roussel Clough in France. We were traveling over there, and Karen, my lovely young wife at the time, went with us, and we were sitting at dinner, and the Tour d'Argent, still there, it's the oldest restaurant in Paris, I think it started in the 1500s. And a very lovely man named Claude Terrail runs the restaurant. And we were upstairs, and we had this very lovely table because we had 4 or 5 top executives who were French, so we were being treated very, very nicely. And Karen's very lovely and sitting there, and there are 2 or 3 of us from the company. And I don't know what the whim caught me, but I, with my limited high school French, called the waiter over, or the maitre d' actually, and told him that Mademoiselle is Karen Carter, the niece of the President of the United States, and that I am a security agent, and please would he be aware of anything? I go, oh yes. I sat down, I thought that was kind of funny. We get nice treatment, the maitre d' was very hospitable. Next thing I know, Mr. Claude Terrail has appeared, and he has his card. And if you look, the walls of the Tour de Jean are filled with cards signed by notables. So Karen signed as Karen Carter, niece of the President of the United States, which ultimately went up on the wall and was there for many, many years. But now this became interesting. The Frenchmen who were with us were getting a kick out of this. They're just sitting there nodding and giving it credibility. And now at one point, they had this great wine cellar. And so the maitre d' had come over and said, anything that Mademoiselle would like to do? I said, yes, she would like to tour the wine cellar, but it's a security matter. We cannot have anyone else down there. Pas problème. They went downstairs, threw everyone out of the wine cellar are the catacombs of Paris that they rented many years ago. They sealed them off, and they kept literally 500,000 cases of wine in there. Cases, not bottles. And so we, the security agents, went downstairs very sternly. We checked the corridors. We sent a message back up. Mademoiselle Karen came down, and now everyone is guiding her and showing her. Everyone's standing there looking very serious. And finally, they seat us down, and they serve us some Armagnac from 1876. And asked us anything Madame would like to do, Mademoiselle would like to do in Paris this evening. Well, Regine's, if you recall, Regine's was the disco at the time. You're talking way back when. And the disco is the place to be. There was a Regine's in New York, not a problem. And so they call up a limousine, they put us in a limousine, they drive us to Regine's. We get out, the security people are holding the mobs back. And they escort us in, and they have reserved a corner area that's now been roped off, the royalty area, and that's where we get to sit. And every time Karen gets up to dance, we all march out onto the dance floor like security people. We have a cordon around her blocking anyone. This went on for about 4 or 5 hours, and it was wonderful. We paid the bill and gave lavish tips because that's what you're doing, you're, quote, royalty. Even though Carter's family wasn't quite royalty, it's close enough. And we get up to leave, and they come rushing over. They've been trying to reach Regine, and they've just got her on the phone. She's down in Monte Carlo, but wants to talk to Karen Carter. So my poor wife had to get on the phone with Regine, told her she loved the restaurant, said next time, I'm back in Paris, we'll talk about a few suggestions I might have. Now we marched out, we walked down the street, turned the corner and collapsed. You had 8 dignified French people and us all rolling around the grass laughing. So it was a great deal of fun.
You have kids?
Yes, we do. I have 2 by the first marriage, both in the police, one here in California and one in Florida, and 2 with Karen.
Any of them going in a scientific direction or entrepreneurial direction?
Yeah, my daughter actually is becoming a doctor of physical therapy. She's now 27, very beautiful, has had some career changes. Started off by loving horses, doing a fantastic job, but it's difficult to earn a living in horses. The trainers earn a living, okay? Right. The contestants earn ribbons, the most expensive ribbons you ever had in your life. And so after that, she decided to become a photographer, went to photography school for 2 years. Superb photographer, but there isn't that much business, but she's had her work with the horses and photography, oddly enough, propelled her into the area of physical therapy. And now she's getting her doctorate. She's got her master's and going on her doctorate, which she'll complete next year. Okay. And Daddy's little girl now gives her massages, and when my back hurts, says, call the daughter, her back hurts.
Good for you. Built-in treatment, huh? Do you have any advice for kids going into sciences these days?
That's an interesting question.
Would you encourage it?
Well, let me recount one thing that may pertain to that. When I first went to RCA, their practice was to take the new people coming in from school and send them out in the field as recruiters. The concept being that they bridge both worlds. In other words, going out there to say, hey, I was in your shoes 2 years ago, and here's what you need to think about, and also to get a better feel for who will be successful. And the key question I always asked was, why do you want to go into research? And the answer I would hear too often was, I want to be creative. And that's when you realize research doesn't make you creative. It's an innate ability. If you are creative, and talk about advice, if you're creative, I don't care if you're a ditch digger, you're going to figure out a better way to dig the ditch. Right. If you're going to build a house, there's a better way to build a house. You're always inventing and creating. Creativity. And so To those people that think going into research will be great because it'll make them creative, it's the flip side of it. If you feel creative and have been creative, then go into research. Okay? In other words, try and judge what you enjoy doing and are good at doing and are happy, and try and follow that path. Now, it's specious advice because you read now about kids. I mean, I went to a scholarship school and all of us never had to pay tuition. We all came from very middle class, lower middle class families. And now I read out there these kids that are coming out of college with a degree that have debts of $30,000, $40,000, $50,000 hanging over them, and the need to start repaying it on an immediate basis.
Yep.
I can't imagine that burden. In all the years that I went to school and all the people that I knew, we made it through one way or another. We either worked or we got a scholarship, or we worked and got scholarships, and that's where the money came from. Student loans, at least as I remember back in those days, didn't exist. You did not come out, you may have come out with a degree, but you didn't have a debt. You may have taken longer to get the degree and you didn't have debt. And I'm not pointing figures, the concept of easy debt for a student, everyone took advantage of. Why not? It's crazy. Everything is wonderful. I'll get a great job. I'll pay it down. They come out in the middle of a recession. They have this enormous debt and they can't pay it off and they can't get a job.
Right.
I've never seen anything like it. So I have to say, any advice I might give, I'm afraid, be tinged by what was and ain't. If you go back in time 40 years, I have some good advice for you. But other than that, no.
I have a personal story. I'll tell you about that later on. My son. What do you think about museums? Are museums important in terms of teaching people about what has gone on before and how you may take advantage of that knowledge?
I believe so, but I believe it's a question of the tail and the dog. You can take, it's almost like that business of the three men in front of that hair screen in the submarine. You get one person will come to the museum and say, oh wow, that's really fantastic. That reminds me, yeah, I have an idea. You have another person come in and look at the same exhibit and say, huh? It's the person. Are the museums important? Yes, they are. They're extraordinarily important because seeing this stuff sparks people, the right people. There are people out there that will benefit tremendously from the museum, and there are people out there that will not. We had a moon rock exhibition out, this is 1973. By that time, I was now chairman of the Physics and Reliability Physics Symposium, it's called. And in 1973 it was, I managed to, we had a lot of support from NASA. We managed to get a moon rock actually out of NASA and on display at the show, at the conference. And it was interesting, we had 25,000 people come past to see that by count, okay, over a weekend. It was the first time a moon rock was ever let out of government custody for any kind of shade. They had not done this because every politician wanted one, every government wanted one. We were very fortunate NASA was able to get this for us, or at least loan it to us for that short period of time. And so people had not had a chance to look at a moon rock. And you had 25,000 people come past it. And I know that because it was the guards on the moon rock had counters, and they counted for every time a person came past. And they fell into three categories. You talk about how people respond. Is the museum important? What is important about seeing a moon rock? You'll see it in a newspaper, whatever have you. And with three reactions. One reaction was, looks like a piece of gravel in a driveway. The other reaction was, I could wear that on a ring. And the third reaction was, wow. And I'll tell you, every guy, the men, what's the fuss? It's a rock. The women, I'll put on a ring. The kids, wow.
Okay.
So when you say is the museum important, you betcha.
Right.
Every kid that walked past that moon rock never forgot it, and it got them excited. It got them excited about science. It's the wonder that kids have. If that can be nurtured, and a museum can do it, I used to love to go to a museum. It was the same thing. It would give me ideas, and it was fascinating.
Sure.
So yeah, you take away the museum, you take away an enormous stimulus factor that I think has shaped a lot of kids over the centuries. So I think the effort you're doing out here is phenomenal. I'm hoping that the work that's gone in, even the oral history that's gone in, hopefully somewhere, somehow, somebody's going to see this,
Sure.
and it'll make a difference. I'm sure it will. And I'm sure you're sure it will.
I wouldn't be spending my time if I didn't think it was important.
You know, there
It's
are
good
people
to
out there that are pragmatic and say, well, no, it is a waste of money. When you got to cut, let's cut this. You're cutting off your future. You're cutting off your future. Mm-hmm. Sure, cut back educational programs doesn't affect the bottom line today, but boy, is it going to ruin us in the future.
Sure.
It's hard to fight it. Hard to fight that thought.
If you look back over your career, Steve, what do you think were the sort of 2 or 3 most significant influences that perhaps sparked something or changed the direction? Or
Ooh.
Obviously, our
What epiphanies did I have? would
yeah,
you say?
that's a better way to put it. Were there any that really
Yeah,
stand out now in hindsight?
when you say insights, I think some of the more creative things, the epiphanies of I had have been mainly technical.
Mhm.
The realization, oh my God, I can store an image in that tube. They were always in those days helped along by a little bit of gin. I was always most creative after a martini.
Right.
Okay, I keep telling my wife that would make me more creative. She says, no, you're down to wine these days. But you're talking about the aha moments.
Yeah.
They've occurred. I'm trying to go back, and they seem to, you're talking about the giant aha moments?
Well, the one you mentioned that may or may not have, you think, is the annealing process.
Yeah.
Yeah,
there've been
the
many.
surface states.
Yeah, that is as a jump, it was no bigger than many others that I've done.
Mhm.
As the consequence of that jump, it was
Yeah.
enormous.
Right.
In other words, was it one brilliant idea that it had other? No, it was just one idea in the right place, right? I got this thought, and we followed through with the thought. And the same thing with the insurance tracking I'm doing, how to do something, use an expert system in a series, they're incremental, but the impact that they have depends upon where they're applied. In the case of the insurance tracking, it was tremendous to me again, because that's a big business. In the case of the Liquid Crystal digital wristwatch, I never made any money out of that in my life, nor at RCA, nor at anyone else really, because by the time the watches became popular, the patent was dead.
But the world benefited.
Yes. Well, I wrote a paper once called Dollars in Science, which actually got published in Vital Speeches of Our Day. I'll send you a copy.
Sure. I'd like to see that.
I like to read it and take lessons. Oh, that's me talking. Well, yeah, that's pretty good.
Anything else you'd like to say, Steve? We're going to cover RCA Labs, the influence on you and the industry this afternoon.
In terms of
with
the
group,
MOS, it's just intriguing. There's a picture that's in. Did you ever hear of? Gosh, I was trying to think of this name of this guy. No, I can't think of it right now. But no, I'll save it for later.
Okay.
I just want to thank you very, very much. It's been a fantastic experience coming out here. I look around, I'm delighted. One of the things about a museum is that so traditionally they contain ancient things. You go to Metropolitan Museum of Art and you look at mummies and you look at great old paintings. The very fact that the computers that I did are in the museum makes me feel so old is beyond belief. It's like a dinosaur touring in the Museum of Natural History and seeing himself there. Oh my God,
Yeah.
am I that old?
The challenge in a museum like this is, when does something become important? And we generally had the rule that, well, it should have been around at least 10 years before we'd accession something in. But it's changing so fast now. We grabbed the Google server after 6 years.
What you're pointing out is really, people pay lip service to it, but I'm really seeing it as a real problem. The rate at which technology is moving now is a serious problem. I'll tell you why. Because the amount of money necessary to create the technology is counting on a payback over a certain period of time, and that period of time is getting lesser and lesser and lesser. One of the things that fascinates me, let's take a good example of the old times. The color television tube. The color CRT was born in 1955, 56, okay, at that company that I knew. The last of them were probably manufactured about 8 or 9 years ago. You could still get color CRT monitors for your computer. They're gone now. So I've lived through the entire life cycle of the shadow mask CRT, which was created in a period of a year, okay, and lasted for half a century. Mm-hmm. And you look at other technology, small technology. A few years ago, they put in automated toll systems throughout the country. And Florida has one called SunPass, and they came out with these transponders. And the transponders are wonderful. You put 2 batteries in them, you clip them on your dashboard, and fantastic. It only took 2 years before they were replaced with a semiconductor chip that was being read, a passive chip that was being read by a monitor above. And now the people who built those transponders put a lot of money into it, the cases, the mechanisms, all gone, no return. And so it becomes a little frightening, because in the sense that it advances so quickly, it then begins to destroy the things that cause it to be funded, if you will.
And causes the decline of the big R&D establishment. Bell Labs, RCA,
Oh, absolutely.
places that don't exist anymore.
Exactly. It's really amazing. I remember every time, and I've been in business for 48 years, we've done successfully, and every customer we've ever had would look at us and say, you're a little company, we're worried about your survival, and they're all gone. We did stuff where Texaco, Lawa, Latin America, West Africa, they had to vet us out. What are we going to do? They disappeared. It's just amazing. RCA is gone, like you said. It's just astonishing how you can be big. That doesn't guarantee security anymore. the thought that you would graduate school, go to work for IBM, and then you could think about your 401k. I actually had, when I went out recruiting, I used to, among people that would tell me, you know, I want to be creative, or only superseded in terms of getting me disappointed by somebody and say, what are the retirement benefits? It didn't really happen.
Right.
One of the things important to me, what are your retirement program? You're just out of school and you're worried about your retirement program?
Yep.
Amazing.
The world has changed, Dave.
You know,
We've
there's
seen massive changes.
Take a look at video. Go back to video again. In video recorders, in particular the media. I think it was 75, 76 was the advent of the first of the home videotape capabilities. There was Betamax and there was VHS. And it was a political struggle. Betamax was a Sony product, and the rest was a consortium in Japan that did VHS. And marketing-wise, VHS killed Betamax, which is a shame because Betamax was actually a better technology, was better resolution, but neither here nor there. And videotape lasted a long time, but somewhere, I would guess in the mid-90s, you began to see the DVD come out. Mm-hmm. And the DVD, so when you go to Blockbusters, you would see 80% of it was still videotapes, but there was now these little DVDs. And the videotapes vanished over a period of 3 or 4 years, 5 years. So now you had just all DVDs. And the DVDs began to become ordinary, so they went to Blu-ray, which is just tremendous innovation, tremendous amount of money, and it's now being killed by streaming.
Yep.
You know, you go on, and you take a look at streaming, and you realize, the thing that's funny, Karen suggested for my son's birthday, I get him a new Blu-ray DVD player. And I researched it, and this one by Sony had this great advantage, LG rather, I'm sorry. It had built into it that direct wireless connectivity, so not only could you play DVDs on it, not only could you play Blu-ray on it, but you could latch into the streaming services, which if you really think about it, destroys the whole need for the DVD.
That's right.
They had to build in order even to stay alive, they're building in the competitor that's killing them.
Which is exactly the Netflix dilemma right now.
That's exactly right.
Sure. I look at just technology, manufacturing integrated circuits, and lithography is one of the most obvious ones. That when we first started building these things, it was a contact printer using
Right,
plates.
exactly.
So one of those would cost you about $9,000-$10,000 if you didn't build it yourself. And the next step was a projection system of some kind. Then projection aligners, and each one went up by an order of magnitude in cost.
Yes.
And the time it was useful for is shorter.
Yes, you're exactly right. You know, there was an interesting, I think this may be off subject, but it was an interesting experience. This is back, the year had to be mid-60s. And there was a conference, this is after the MOS had been announced, and Cyril Hilsum, who was head of the Royal Radar Establishment, was hosting a conference, international conference on electron devices, somewhat different than the domestic one we had here, and invited people from around the world to come and give papers. And I was going to be one of the participants. And the MOS transistor was out. We still built our own diffusion furnaces. This is really funny. You couldn't buy them. You had to build them. Now it's an industry. But anyway, I got a call, and they said, do you need to go over to Building 3 and talk to some people over there? Now, Building 3 was the building that RCA did its government confidential secret work in. And in all the years those RCA laboratories, I never had set foot in it. And so I went over, was curious, and I was invited into the office. And one of the managers over there, who I knew, introduced me to this fellow named John. And John is with the government, and we have a request to make of you. I said, the government didn't offer me a card. He said, you're going over to a conference that's going to be internationally attended. Now, we're really keenly interested, and John is keenly interested, the government's keenly interested in understanding just how far the Russians have come in MOS technology. We have no idea, because that's really critical in terms of computing power and supercomputers and a whole bunch of things. And I'm really beginning to feel, yes. And we explained to John that you're not an activist, you don't mind asking to do this. I said, no, politically, that's quite fine. I love you, I love this country. Anything I can do to help, what is it? They said, well, look, don't be James Bond. Don't ask any questions, don't make any leading remarks. If you happen to hear something interesting, just make a note of it, maybe write it down to remind yourself, that's all. Let us know when you get back, but please, don't do anything. Don't be brave, you're not a secret agent, just keep your ears open. So I go over, and the first night is a cocktail party. And Cyril is a very graceful host, and one of the people standing with a little group of us talking is this fellow from Bulgaria. I don't even remember his name, but which was at that time an Iron Curtain country. And he's standing there talking, and he's chatting, and he says, you know, it's so ridiculous. He says, I go to Moscow last week, and I want to see what they're doing. They don't even have a diffusion furnace yet. How am I going to make anything? They have nothing. Says, thank you.
That's all the information you need.
That's it. And I went back, and I told him that. And guess what? They landed a MiG in England a couple of years after that. It wasn't any MOS on it, just tubes.
Yep.
So They remember that the loose lip sync ships. You never know.
That's for sure. Okay,
That
Steve.
was
well,
my
you've
role as
got-
James Bond. I got to be 001. Never made it up past that.
There we go. And I hope we've saved a few stories for this afternoon, and we can talk with the group about RCA Labs. So.
Yeah, I apologize. My voice has become somewhat hoarse, but it reminded me of a story. I did some work in Scotland with Nuclear Enterprises, part of the ultrasound imaging. So we used to commute back and forth. And the Scottish have this absolutely marvelous sense of humor. And the story I'm about to tell you, which as best I can remember my Scottish accent, you got to remember when they told the joke, they didn't hear it with an accent. And so anyway, McDougall comes into the office and says, "Good morning, everybody." And they say, "McDougall, what's happened to your voice?" "Oh, God's playing golf." "Yeah, how God's name did you get up playing golf?" "Well, you see, on the golf course, I hit this tremendous drive. It was 300 yards, it was a foot. But there it is in the rough. So I'm in the rough looking for my ball, and some young lady's looking for her ball. And suddenly, up ahead, I see a cow. And stuck in the cow's arse is a golf ball. So I walk up to the cow, and I pick up the cow's tail, and I look at the ball. But the ball's a Slazenger 2, and I'm playing a Slazenger 3. So that's when I turned to the young lady and I said, "Excuse me, miss, but does this look like yours?" That's when she hit me in the throat with the golf club. I like that.
Okay. Thank you. I think that's a good moment to stop.
Okay.